All right. I thought it'll be good to start off by giving you guys a little recap of where we are today, just 2 years or so after launch. So here's a little brief overview.
Roger. Proceeding with the count.
T-minus 10, 9, 8.
7, 6, 5, 4,
3, 2,
1.
Am I confident that she's going to go and she's going to be successful? Absolutely. It's going to go and she'll be good.
Things are looking good. Coming up on entry. Vehicle reports entry interface. At this time, it'll begin pressurizing the propulsion system to increase the thrust of the system. We'll use that for all the maneuvering in the atmosphere we're about to do. We are standing by for guided start of guided entry. We are beginning to feel the atmosphere as we go in here. The vehicle has just reported via tones that it has started guided entry. At this time, the vehicle is beginning to steer its way to the target. We have seen peak deceleration. It is starting its first mag reversal. It is reporting that we are seeing G's on the order of 11 to 12 Earth G's. Mag reversal 2 is starting. We are now getting telemetry from Odyssey. We should have parachute deploy around Mach 1.7. The parachute is deployed. We are decelerating. Heat chill has separated where we found the ground. We're down to 90 meters per second at an altitude of 6.5 kilometers and descending. Standing by for backshell separation. We are in powered flight. We're at altitude of 1 kilometer descending. Standing by for sky crane. Sky crane is started.
signal to us, you remain strong.
Touchdown confirmed. We're safe on Mars. Time to see where curiosity will take us.
Got thumbnails.
What a fantastic demonstration of what our nation and our agency can do. I could only think of the words of Teddy Roosevelt as I was sitting there. It is far better to dare mighty things even though we might fail, than to stay in a twilight that knows neither victory nor defeat.
Within 2 months, the team found an ancient riverbed, evidence of flowing water.
We have found a habitable environment that is so benign and supportive of life that probably if this water was around and you had been on the planet, you would have been able to drink it.
We've got a long mission ahead of us, and because of that and the capabilities of this rover, we have this possibility for just monumental science accomplishments.
All right, so I hope that gives you a pretty good overview of what we've been up to in the 2 years that we've since launch just after Thanksgiving in 2011. And so what I wanted to do was give a little bit of overview of, as you saw in that video, all that the rover has been doing has come down to Earth in the form of data. And I wanted to talk to you a little bit about the piece of the flight software that manages the data on board the rover. It's called the data management subsystem. And it's kind of funny when we talk about Curiosity to think about the piece of the flight software or flight software for the mission, because in fact Curiosity, as many of us on the team understood, is not really a single mission. It's often been referred to as 3 missions in one. There's the cruise phase of the mission, where we go from the launch pad to the top of the Martian atmosphere. There's the EDL phase, where we go from the top of the Martian atmosphere to the surface of Mars. And then there's the surface phase, which is where most of the science happens, which is when the vehicle actually becomes a mobile roving laboratory. And designing software, all of flight software in general, and even a particular subsystem like the data management subsystem, which has to cover all phases of the mission, has its challenges. And I wanted to talk a little bit about some of the challenges we faced and how we try to go about addressing them. So to give you a little intro into how what data management on Curiosity is like, here's all you need to know about what the rover Avionics is in terms of the data management on the rover. So we have what we need for data management is 3 things. We need processing power, we need memory, and we need a way to send it to the ground. And those pieces are on this picture. For the processing power, we have 2 Rad 750s. Curiosity is a dual string spacecraft, so we have a prime and a backup computer. And those are Rad 750s, radiation hardened computers. We have memory, and we have both RAM, and there's RAM on the Rad 750, about 128 megabytes of it. And we also have off-board RAM, which is sitting on the PCI bus, which we can access. It's a bit slower than the main Rad 750 memory, but we use it extensively. So that's volatile memory. And then we have non-volatile memory, which is flash memory. It's 4 gigabytes on each computer, and that's NAND flash memory. And then for talking to Earth, we have 2 telecom subsystems. We have the X-band subsystems, which uses the low gain or the high gain antennas, talk direct to Earth, but it's low bandwidth. When we are close to the Earth, it's you can measure it in kilobits per second. But once we are on Mars, it's around hundreds of bits per second. When the geometry is right, we can get up to about 1,000. But so most of the data that actually comes down from Curiosity comes down through the overhead relay orbiters. There's 2 relay orbiters around Mars right now. There's Mars Odyssey and Mars Reconnaissance Orbiter, MRO. And those Curiosity can talk to using UHF and a much higher bandwidth, with MRO up to 2 megabits per second. OK, so that's the avionics. Now, in terms of the data that actually comes down from the spacecraft, there's 2 kinds of data that comes down. There's something called real-time telemetry. And real-time telemetry is really only or mostly important during cruise and also partly during EDL. What happens here is that as the software is running on the spacecraft, it's collecting a lot of data. So there's 2 kinds of data that we distinguish between. There's something called EHA, which is, think of these as periodic measurement samples. So you can imagine a sensor that's reading a temperature and it's sampling the temperature at some particular rate. You could also have something that's measuring how much memory is left, say, on your file system. Or something that, in this particular example I've shown here, we have monitors that tell you what the CPU utilization is. How much of the CPU are we using at this instant of time? And so those measurements are just being taken, and they are being sent out they're being streamed out whether or not somebody is listening. And so during cruise, usually somebody is listening, and happens to be the ground. When you're on surface, usually nobody's listening, and I'll talk about that a little bit later. The other kinds of measurements we take are these things called discrete event logs, called EVRs in MSL parlance. And these are essentially whenever an event happens of some interest, the software just announces that event, and it's written out. In this particular case, you can think of it as a printf that's recorded. And again, this thing is these EVRs are being streamed out in real-time telemetry. Now, as I said, real-time telemetry is only important if you're actually in active communication with either the ground or with one of the orbiters, which once you're on the surface, that doesn't happen very often, as you'll see in a minute. And so the vast majority of the data that comes down from Curiosity comes down through something called recorded telemetry. And recorded telemetry, as you might expect, is essentially data that's stored in non-volatile memory, and then it's sent to the ground only when there's a definite link that's been established, or there's a definite path through which Curiosity can send the data to the ground. And there's two kinds of recorded telemetry. There's a real-time telemetry. So I said earlier that real-time telemetry is streamed out. The EHA and EDRs are just being streamed out whether or not anybody's listening. Well, they're also forked into the recorded telemetry stream. So all the EDRs and EHA that is being generated are also saved to the non-volatile memory so that they can be replayed back, so that we're guaranteed that we don't lose anything. And then there's the vast majority of the data which comes down as something called data products. And data products are really single pieces of data, single data objects that are created in response to science or engineering activities. So you can think of, in the video you saw, we have data from the 10 science instruments we have on board, the 17 cameras we have on board. All that data comes down through the data product stream. They're essentially, you can think of them as files that are being created by the rover software and then written to the NVM, and then eventually, when there's guaranteed link between the rover and Earth, they're sent out. And all that is being managed by this piece of software, the data management software subsystem. Okay, so I talked about the phases of the mission, so let me sort of summarize the three phases again, but this time from the point of view of how it looks to the data management subsystem. So the first phase of the mission is cruise, and that's about 8.3 months. And as I said, the objective of the cruise phase is to get from the launch pad to the top of the Martian atmosphere. And the best way to imagine what happens in cruise is you're really trying to reach a certain point in space. And at the top right of the picture, you can imagine that there was this little rectangle about 11.5 by 2.8 kilometers in size, and the job of the GNC team was to go through that rectangle. And if they made it through that rectangle, then we were able to meet our objective of landing right next to that big mountain that's in the middle picture there. And you can see that little, on the top right picture, that little orange dot that tells you how far off they were from being right in the middle of the center. So it's an amazing job by the GNC guys. And at the bottom right, you see that most of the time when we are in cruise, the rover is packaged up inside, and we are just talking to the rover through its X-band radios. The UHF radios have nobody to talk to. And the X-band radios, I'll come back to this in a minute. Essentially what happens is that we request time through the Deep Space Network, and then we are able to, if we are in active link, we can get the real-time telemetry, and if we are not in an active link, then the real-time telemetry, as I said earlier, is just being streamed away, is being essentially dropped on the floor. But we can get all of that telemetry because whenever we are in an active link, we can request the recorded data stream, which remember is being saved to non-volatile memory and can be fetched on essentially by ground command. Okay, so that's the cruise phase. The second phase of the mission was EDL. And this, I'm sure many of you have heard about this. It's called the 7 minutes of terror. You're going at, 13,000 miles an hour from the top of the Martian atmosphere down to 0 on the surface in 7 minutes. From a data management point of view, EDL is interesting because there are really two big drivers to what we need to do during EDL. The first is we have to account for the possibility that that we may actually not succeed. This was the first time a sky crane maneuver was being executed on another planet. So we had to make sure that if it failed, we had to have enough telemetry so we could learn lessons for the next time. And so that drove essentially the design requirement that during those 7 minutes of EDL, we had to have data coming down to the ground all the way till we reach the surface. And the way we achieved this was there's really two streams of data. There was one stream of data coming down through the X-band subsystem, which were just tones. Because of the way the X-band subsystem works, you can't really get much bandwidth when you're going through these crazy maneuvers, trying to get down to the ground. So what the spacecraft was designed to do was to send beeps, essentially beeps of different frequencies saying when certain critical events had happened. Now, the one complication was that because of the way we had the landing site geometry work, right after parachute deploy, which you saw in the movie, the Earth set over the Martian horizon. And so we lost X-band communication right after parachute deploy. So we got X-band tones right through them. And so the rest of the telemetry that came down through the two orbiters. So they were both Mars Odyssey and MRO had been scheduled to be flying right over MSL, right over Gale Crater where we landed during those 7 minutes that Curiosity was descending. And you saw that picture in the video where MRO actually got Curiosity floating on the parachute on her way down. And so the data management system is essentially designed to stream this data during those 7 minutes. But the second piece of the design requirement was that, well, what if the landing is successful? But in that case, we've collected a lot of really valuable data on our way down. And so what we want to make sure is that all that data, which is most likely, because it's only 7 minutes, we've collected and it's stored in volatile memory. We have to make sure that it's transferred to non-volatile memory so that it's safe. And then we collected a lot of data. We couldn't get it all down right away. And so over the next few weeks and days, we would be able to get all of this really important data, because this data is worth its weight in gold, because we've now successfully landed on the surface of Mars, and we really need to make sure we get all of that data done. So that was the second big design requirement on the data management system. Okay, and then the third phase of the mission, which is really the most important phase from the science perspective, is the surface phase. And this one, we hope, will last for years and years. And this picture really just shows you what a typical day on the surface looks like. So at about 10 o'clock local Martian time, which is on the bottom, so you can see Mars time on the bottom, Earth time on the top, and we shift every day by about 40 minutes. The rover wakes up in the morning, and of course, because the Earth is between Mars and the Sun, if you want to see where the Earth is from Mars, you just look towards the Sun. And so around 10 o'clock in the morning, it looks for the Sun, and it waits for a sequence of commands which tells it what it's going to do that day. And so it gets an uplink from the Earth with all the commands saying what the rover is supposed to do that day. And then it goes off and does all those experiments. It drives, it samples rocks, it drills holes. You saw some of that in the video. And then about 4 p.m. in the afternoon, it gets an orbiter overflight, MRO or Odyssey, and it's about 10 minutes long. And the rover sends its data, all the stuff that's happened that day, sends that to the orbiter, and then possibly, in order to recharge its batteries, it goes to sleep. And then sometime in the morning at around 2 o'clock, it'll wake up again, and it'll know that an orbiter is going to go over the sky. And so it'll wake up at 2 in the morning, talk to the orbiter for 10 minutes, go back to sleep again. And usually it does that more than twice a day. Usually we have 2 orbiter overflights in the afternoon and 2 in the morning, though this varies a lot. So that's the cadence on the ground. It's the rover is going through these sleep cycles, doing its work during the day, sleeping at night. Sometimes it does experiments at night, like you saw the nighttime Mali image in the video. So three phases of the mission, 3 very, very different sorts of needs for the data management system. So just to summarize here, in the cruise phase, we are building these recorded data products while ground is not in link with the spacecraft. When we are in an active link, we want to make sure that the data comes down, and it has to come down in priority order. We have to make sure that we get the important stuff first. Remember, there are 2 computers, so we have to, while we are flying in cruise, both computers are on, and the backup computer is also collecting telemetry. And so even though most of the work is the actual work of the maneuvers and so on is being done by the prime computer, we want to make sure that the backup is healthy, because that is our safety net. And so we have the part of the software's job is to be able to talk to the backup computer and get data from that backup computer and then stream it down to the radios. And then you sort of have to do these housekeeping jobs of reprioritizing products that you've decided are no longer that high a priority, retransmitting it. Sometimes we have losses on our way down from the radios to the ground. So we want to ask the rover to resend something that we didn't get completely, and then delete, of course. We want to make sure that the non-volatile memory is going to start filling up. So we ground sort of actively commands deletions. During EDL, I already talked about this. One of the key things that happens during EDL is that there are, as I'll mention a little bit later, there's a lot of stuff going on, 7 minutes, but a lot of activity. And we want to make sure that all of that data is being saved properly, and you know, the software is designed right and does its job right. And I'll talk a little bit more about that. And as already talked about, we have to send the data to the orbiters in case something goes wrong, and then we have to make sure that the data is safely saved on non-volatile memory before we start our surface activities. And then once we are in surface, it's a very different mission. We're going to sleep and waking up 5 times a day. We are not talking to the Earth most of the time. The only time we actually send data is through the orbiter. So almost all our data that comes down from Curiosity, more than 99% of it, comes down through the orbiters. We get almost no data directly from the Earth. The Earth to Curiosity link is almost exclusively one way. It's commands being sent from Earth to Curiosity. And then there is, so we have to get ready, the rover has to get ready for an orbit overpass and then get ready, package all the data to send it to the ground. And that's the job of the data management system. And then there's this new features in the rover software for things like something called virtual data products, which are basically images that are sitting. So as I said, we have 17 cameras. Some of those cameras have their own flash memory. And so when they take images, the images are actually stored on the camera. And the rover just stores a little stub that says there's an image on that camera. And now when we are getting ready for an orbiter overflight, the rover essentially just in time pulls that data in and packages it up and sort of does this right while while it's getting ready for the orbiter overflight. So the software that has to manage all of this activity and manage all these different sort of almost orthogonal requirements it's a challenge to get it right because of what we have to work with. So I said we are using the RAD 750. If you look at the processor speed, this is not really a modern processor. It's a 133 megahertz processor, has 128 megabytes of memory. If you compare that to what you're carrying in your iPhone or on your smartphone today, you'll see where we are relative to the current technology. But in spite of having a fairly limited processing power, fairly limited memory, we have a lot of requirements. I've already shown you a sampling of these. And so it turns out we ended up with over 60-something level 3 and level 4 functional requirements. I haven't talked about many of them. But I wanted to touch on 3 of them, which I thought would be illustrative of the kinds of different challenges we had to deal with in getting the software ready and some of the lessons we got. The one, and I'll talk about the 3 ones in the middle, those 3 big bullets that are in the bottom of the slide. But the one thing I want to mention is, and everyone who's worked in mission software knows this, the big driver in all of this is hard deadline, right? You have a mission to Mars. There's a launch deadline. You don't have the option typically for a launch slip, though we did slip once in MSL. But you can't, when you're designing the software, you have to be ready to meet that. And so how do you design your software, and how do you try to test it and manage what you're doing in order to achieve all these objectives? So let me talk about a couple of these challenges. So the first one is Curiosity was designed to, or one of our key requirements was to support 300,000 products on the rover at any time. Now, if you go back and look at previous missions like MER, they're typically tens of thousands was considered a big number. We are going up by an order of magnitude. And if I tell you what if you compare the processor speed and the amount of memory we have compared to MER, MER had the same amount of memory. And that was a mission that was 10 years ago. So it's challenging to be able to achieve this. So how do you work with something like this? The problem is that the data management software, it's managing this large set of data products, 300,000 data products potentially. It has to do a whole bunch of different activities. It has to downlink data. So while we're getting ready for an orbiter overflight, what does it have to do? It has to find the highest priority data product that has yet to be sent, find the oldest one, because we want to see the oldest ones first. We have to handle requests from the ground for reprioritization. Now, reprioritization, usually the ground gives a range, and now you have to find all the products that match that particular range. There's a requirement for doing something called auto-deletion, where if the rover memory starts filling up, we have to start automatically deleting things so that we can, because we don't want to lose new data at the price of old data. So we want to be able to delete old data if ground for some reason is not in the loop and is not managing the resources properly. We want to make sure that the rover protects the non-volatile memory and keeps enough room available for new stuff. So there's a challenge in how do you design software to meet all these, to manage such a large number of data products while achieving all these functions. Now, if you step back and think about this from a computer science point of view, this is not it's a solved problem in some sense. We know how to manage large data sets, right? But the problem is that it's one thing to say we know how to manage a large data set if you had enough memory and enough resources. But when you don't have that resource, then what do you do? So for instance, just to give you an example that we ran into in Curiosity, the standard way to manage a large set of products, and you want to do a search, or essentially a selection, the usual way to do this efficiently is to basically use a balanced binary search tree. The problem is that if you look at the standard implementation of a balanced binary search tree, it's, for instance, you can look at red-black trees. It requires 3 pointers per node. Well, we are supposed to support up to 300,000 products. So we have a tree with 300,000 nodes in it. You do the math. You need about 2.7% of your RAM for every tree that you have. And we have multiple trees because we have to support search criteria that have multiple. You can search by oldest product, newest product, highest priority, a range of things, and so on. So that was one of the challenges. And of course, the only way you can meet the challenge is try to come up with some optimizations. And so we found this nice variation of binary search trees called Anderson trees, which, by the way, are wonderful. If you ever get a chance, if you ever have to do this kind of thing, if you read the paper by Anderson, it's a really great paper, a very well-written paper explaining how you can do this. And so we had to tweak this a little bit to make them more efficient, and so we got it down a little bit. But now this, of course, makes the code a little bit more complicated, and now you have to worry about testing it. Come back to that in a bit. Okay, another challenge, predictable behavior. We have to make sure that the software has really strict bounds on worst-case performance. Give you an example. EDL, as I mentioned, 7 minutes, there's a lot of stuff going on. MSL flight software has about 140 threads running concurrently. They're all running at different rates. Some are running at 64 hertz, some are running at 8 hertz, some running at 1 hertz. Some are background tasks. They don't have deadlines at all. Any subset of them may be wanting to create data products at any time. And the way we create data products in MSL is that the task, just taken an image or just gathered a sample from the SAM instrument. It's going to take that data and it's going to write it as a file. Now, because our memory is limited, we write that data to the RAM file system or to volatile memory, because volatile memory is fast, and we want to be able to get that data out from the instrument and into a data product quickly. And then we have to free up the memory because we have a very limited amount of memory to work with. So we start doing this process in the background, and the software does this automatically, copies it to the non-volatile file system. The problem is that we have, as I said, these different threads running at different rates, all wanting to write to this shared piece of volatile memory. And the way that we organize the volatile memory is we implemented our own RAM file system. And one of the key things that we needed is, if you think about how people normally implement a shared memory resource, right? You have a single shared piece of shared memory, and you have, say, three tasks that want to access it. The usual way is you have to make sure that the access is thread safe. And the common way to do this is use a semaphore or some kind of a locking mechanism that says somebody can grab ownership of a piece of the memory, and then the semaphore protects somebody else from corrupting it. The problem is, if you have threads that are running at multiple rate groups, like 61 running at 64 hertz, and this is happening during EDL. You can't use the semaphore mechanism because you run into this standard problem where the 64 hertz thread wants to use a resource that's currently being held by the background task. And now the 64 hertz thread either has to drop its data, which we don't want to do because this is EDL, or it has to wait. And there are mechanisms like priority inversion, safe semaphores, but those really don't solve the problem. The 64 hertz thread cannot complete its job. And so we ended up having to essentially rewrite our own file system that provides certain guarantees. For instance, it provides a guarantee of wait freedom. Wait freedom is this nice property that says that if you have multiple threads that are accessing a shared resource, then none of them depends on the other ones at all, not even through any semaphores. And I won't go into the details of how that's done, but that's something that, again, we needed to implement in order to achieve this key property that allows us to have decoupled behavior at the high level during critical events such as EDL. So again, here's a place where the software now gets a little bit of complexity, even though, as Gerard said, we really wanted to keep things as simple as possible. There are places where that simplicity is, you're forced into doing something that's a little bit more complicated because that's the only way to meet a certain high-level objective. So the third problem that I wanted to talk about is the idea that so we have a non-volatile storage, which is NAND flash memory. And if you're familiar with NAND flash memory, it's inherently unreliable medium. And what we wanted to do was make sure that we implemented a mechanism that would allow us to use this memory in a way that was reliable. And so in particular, what we wanted to do was implement a storage mechanism that would allow us to write things to the non-volatile memory. Now, the one thing, as Gerard said earlier in his keynote, one way we can, one principle that lets you address when something goes wrong is to reset the spacecraft. And the idea is, as Gerard said, resetting the spacecraft gets you to a known state. The problem is that's true for all the state that's in volatile memory. It's not true, as we saw in the Spirit Sol 18 anomaly, for the state that's on the non-volatile memory. The non-volatile memory, by design, is not something that you can get to a known state by doing a reset. And so what you have, when you implement something that's on non-volatile memory, you have to make sure that if you took an unexpected reset, when you come back up, the non-volatile memory, the state of the non-volatile memory, in this case, the state of the flash file system, is consistent. So how do you achieve that? So let me give you a very quick summary of why flash file systems are hard. Now, this is a well-studied problem, and lots of people have looked at this. And it's really the basic problem with flash file system is that there's an asymmetry between the write and erase. So if you write to a flash memory, you write in terms of these things called pages, which are 4 to 8 kilobytes in size. But when you want to, you can't overwrite a page that's already been written. The only way you can reuse a page that's been written is to erase the whole block. And the block is a different granularity. And so traditional file systems store their metadata in things called superblocks, which are at standard locations. The problem, you cannot do that with a flash file system. And that one sort of feature or one idiosyncrasy of flash memory is what drives a lot of the complexity of a flash file system. And the property that we wanted to implement was this idea that the flash file system is what, as I said, should be what's called reset reliable. So that if you're in the middle of an operation and for some reason you took a reset because some tasks for somewhere else failed an assertion, we want to make sure that when we come back up, the file system is still consistent. And so we call this reset reliability, and the standard way to state it is that every single operation of the file system should be atomic, even across an unexpected reset. So again, now we have a piece of software that's gotten a little bit more complicated because we want to make sure that it has this particular property. How do we achieve this? Well, the way we tried to achieve this particular property was we knew that the file systems are notoriously hard to get right. And they have to be right because, as I said, the standard fault response of taking a reset to get you to a known state doesn't work for a non-volatile file system. How do you try to build a piece of software that tries to be really as robust as it can? So we basically came up with a test method that used randomized testing. And here I've tried to sort of summarize how that system works. So what we did was we built a reference file system, which was a very small piece of software that had the same API as the real file system. And what we did was we followed, in this box on the top left, you see essentially what the test harness looks like. What the test harness does is it randomly picks an operation. Think of like create a directory or write to a file. It then applies that operation both on the flight system and on the reference files and on the reference system. And then it checks that the two results are the same. And so if you think about it from a test point of view, you're running a random sequence of operations on two file systems that are essentially going in parallel. And at every step, you're checking that the two file systems are consistent. The thing that makes it interesting is that you're also injecting faults. On one branch of the testing is the real flight file system, and what you're doing is randomly injecting faults like resets into the real file system, and you're making sure. And you don't inject those faults in the reference because the reference doesn't have to be robust. The reference is something very simple. And remember the property of atomicity. It tells you that if you took a reset during an operation, then in the real file system, the effect should be as if the operation either happened completely or didn't happen at all. And so you can easily map it to the reference because you either perform the operation on the reference or you don't. And the reference doesn't have to be tolerant at all. And so we can run this sequence of operations over and over, and we did. And so we actually wrote a test harness that would run this loop billions and billions of times on multiple machines over weekends. And we found lots and lots of interesting issues using this, and it really was very, very effective. And so the advantage of this test harness is that it's simple to set up and maintain. And we ended up using a model checker as a test driver, but that's not so important. The most of the hard work is in building the reference. Once you've built the reference, then getting the test harness is easy to get. It's easy to parallelize. You can imagine because we are running these random tests, you can find as many machines as you can that nobody's using at night, and you run these parallel tests across all of them. And it was surprisingly effective. We found lots and lots of bugs that would not have been caught in system tests. And my favorite is a caching bug that we found after launch, but before surface, that would have resulted in all file accesses failing silently after 80 solves on surface. And I'll give you details offline if you want. There was no way we would have caught this with our test mechanism, because it requires 80 reboots. We don't run. Actually, it required 300 reboots. Sorry, 80 solves, 4 reboots a solve. So we don't run tests that have 320 reboots in them. But that was caught by the test harness. Now, there was one failure, I must admit. There was a bug that we actually had on Sol 217 that caused the spacecraft to go into safe mode. And it was frustrating because this was the kind of bug that the harness should have caught. And later we were able to tweak the harness so we could able to catch it, but it was missed. And it was a complicated scenario because it required 2 reboots in the middle. So just in summary, the way we tried to address the challenges in the data management software was to run, we really used randomized testing very, very effectively. Now, we didn't use it, we weren't able to get it to work across the entire functionality of the data product system because it's a little, the reference is really hard to set up. But for the file system, we were able to set it up, and it really paid off in a big way. There were some challenges. For instance, if you run a randomized test overnight, what happens is that you get many, if there's a bug, you farm this randomized test across 20 CPUs, and all of them find the bug. And now you end up in the morning with 1,000 bug reports, and of course, most of them are the same thing. And so you have to be able to write some scripts and find some clever ways to figure out which ones, when you get bug reports, which ones are the same bug. There's one issue where, well, eventually you get to a state, hopefully, where no more bugs are being found, and now what do you do? And so there are some ideas on how you can do this. And the last one I already mentioned, which is, in order for this strategy to work, you need a reference, and building the reference can be somewhat expensive. I will stop there. There are questions.
The testing, Michael McDougall, Grammatech, the testing you did for comparing the two implementations, was that strictly just a dynamic test comparing execution state after 2 runs, or did you incorporate some static analysis?
No, that's, that particular test is just dynamic.
For the tree kind of solution that you used, there was an implicit requirement of performance, I guess, that you mentioned. Like you chose a tree that used less memory, but if you used a naive solution, like how much worse would the performance have been for getting the data?
So unfortunately, we started off with a naive solution. And what happened in test was somebody created tens of thousands of data products, and they decided during ATLO that they needed to deprioritize them because they were about to start a new test, and they didn't want the old products to be at high priority. And they sent a command, and then an hour and a half later, they were still waiting for the command to finish.
Okay.
And so, yes, it was a forced decision in some ways.
Other questions? Nope. Nope.
Temesgen Kazai Nasaims. I want to ask about the reference implementation and the correlation with the real implementation. So why don't we just start from the reference implementation and basically try to preserve those, if you have some invariants, preserve those invariants through the compilation and use the reference implementation as the real implementation instead of later on doing the randomized testing?
Yeah, so the two key reasons. I didn't really mention it. One was that the reference implementation was only for RAM. It was a RAM file system, not a non-volatile file system. The real file system, the part of the problem is you have to deal with all the complexities and the idiosyncrasies of flash memory. The other key piece was that the reference file system did not have to be robust with respect to, say, unexpected resets, because it was never subjected to unexpected resets during testing, because the real file system was atomic. And that simplifies the design a lot.